Beyond the event horizon, peering into a black hole's edge. At the edge of a black hole lies the event horizon, a boundary where space and time collapse. This is not a physical surface you could touch, but a point of no return, a one-way door in the fabric of the cosmos. Imagine a river flowing gently, then quickening its pace until it cascades over a colossal waterfall. The event horizon is the lip of that cosmic waterfall. Once you cross it, the current of space-time itself pulls you inexorably toward the center. Nothing, not even light, the universe's ultimate speedster, can escape its pull. This fundamental truth is what gives a black hole its name. It is a region of space that has become utterly disconnected from the rest of the universe, a pocket of darkness from which no information can return. The laws of physics as we understand them are stretched to their absolute limits here, creating a laboratory for the most extreme conditions imaginable. For centuries, this concept existed purely in the realm of theory, an elegant but terrifying solution to Einstein's equations of general relativity. Carl Schwarzschild first calculated this boundary in 1916, envisioning a point where gravity becomes so intense that the escape velocity exceeds the speed of light. For decades, it remained a mathematical curiosity, a dark star, as early theorists called it, too strange to be real. Yet, as our understanding of stellar evolution grew, scientists realized that these objects were an inevitable consequence of the death of massive stars. When a star at least 20 times more massive than our Sun exhausts its nuclear fuel, it can no longer support its own immense weight. The core collapses catastrophically under its own gravity, crushing matter into an infinitely dense point known as a singularity. The event horizon forms around this singularity, its size, the Schwarzschild radius, directly proportional to the black hole's mass. For a black hole with the mass of our Sun, this boundary would be a mere 3 kilometers in radius. For a supermassive black hole like Sagittarius A at the heart of our Milky Way, it spans millions of kilometers. Scientists are now using powerful telescopes to capture its shadow and decode the mysteries hidden within. Direct observation is impossible, as no light emanates from beyond the horizon. Instead, astronomers look for the black hole's silhouette against the bright, swirling disk of matter that surrounds it. This is the accretion disk, a chaotic maelstrom of gas, dust, and stellar debris heated to millions of degrees by friction and gravitational forces as it spirals inward. This superheated material glows fiercely across the electromagnetic spectrum, particularly in X-rays and radio waves, providing a brilliant backdrop. The Event Horizon Telescope, EHT, a global network of radio dishes, was designed specifically for this monumental task. By synchronizing observatories across the planet from the mountains of Chile to the ice of Antarctica, the EHT creates a virtual telescope the size of Earth itself, granting it the unprecedented resolution needed to resolve an object so distant and compact. In 2019, this global collaboration achieved the seemingly impossible. They captured the first-ever image of a black hole's shadow. The target was the supermassive giant at the core of the galaxy Messier 87, some 55 million light-years away. The image revealed a dark central region, the shadow, encircled by a lopsided, blazing ring of light. This ring is not the event horizon itself, but rather the path of photons that were bent, captured, and redirected by the black hole's extreme gravity. Light from behind the black hole is warped around it, creating what is known as an Einstein ring. The dark patch in the middle is the shadow, an area twice the size of the event horizon, representing the capture cross-section for light. This historic image was not just a picture, it was a profound confirmation of Einstein's theory of general relativity in one of the most extreme environments the universe has to offer. The size and shape of the shadow matched the predictions with remarkable accuracy, providing tangible evidence for a concept once confined to chalkboards and thought experiments. A few years later, the EHT collaboration released a similar image of Sagittarius A, our own galaxy's central black hole, further cementing our understanding of these cosmic behemoths. Studying this frontier pushes the boundaries of our knowledge, forcing us to confront the deepest paradoxes in physics. One such puzzle is the information paradox. According to quantum mechanics, information can never be truly destroyed. Yet general relativity suggests that anything falling into a black hole is lost forever, its information erased from the universe. Stephen Hawking proposed a potential resolution with his theory of Hawking radiation. He theorized that due to quantum fluctuations near the event horizon, pairs of virtual particles are constantly popping into and out of existence. Occasionally, one particle from a pair might fall into the black hole, while its partner escapes. To an outside observer, it would appear as if the black hole is slowly radiating energy, and over unimaginable timescales, evaporating. Hawking suggested that the escaping radiation might carry the lost information in a scrambled, encoded form. This idea remains one of the most hotly debated topics in theoretical physics, linking the disparate worlds of quantum mechanics and general relativity, the two pillars of modern physics that have stubbornly resisted unification. The event horizon is the battleground where these two great theories meet, and potentially, where they might finally be reconciled into a single cohesive theory of quantum gravity. The environment just outside the event horizon is a realm of truly bizarre phenomena. The intense gravity warps space-time so severely that time itself behaves differently. An observer watching a clock fall toward a black hole would see its ticks slow down, a phenomenon known as gravitational time dilation. As the clock approaches the horizon, it would seem to slow to a complete stop, appearing frozen in time for all eternity, its light stretched into longer and redder wavelengths until it fades from view. From the perspective of the clock itself, however, time would pass normally, and it would cross the event horizon in a finite amount of time, unaware that it had passed the point of no return. This discrepancy in the perception of time highlights the relativity of our universe in its most extreme form. Furthermore, the immense gravitational gradient near the horizon creates incredible tidal forces. An object falling in would be stretched and squeezed in a process graphically termed spaghettification. The gravitational pull on the part of the object closer to the black hole would be so much stronger than the pull on the farther part that the object would be torn apart, atom by atom, long before it reached the singularity. The study of the event horizon also offers insights into the most powerful and energetic events in the cosmos. The accretion disks surrounding supermassive black holes are the engines that power quasars, the most luminous objects in the universe. As matter spirals inward, immense magnetic fields are generated. These fields can act as cosmic accelerators, channeling a fraction of the infalling material into colossal jets of plasma that are ejected from the black hole's poles at nearly the speed of light. These jets can travel for millions of light years, blasting through intergalactic space and influencing the evolution of entire galaxies by heating gas and regulating star formation. By observing the dynamics of matter near the event horizon, we can better understand the precise mechanisms that launch these incredible structures. It is a cosmic dance of gravity, magnetism, and matter, choreographed on the precipice of oblivion. The EHT's images are beginning to reveal the magnetic field structures at the very base of these jets, providing crucial data to refine our models of these galactic powerhouses. As our technology advances, so too will our ability to probe this enigmatic boundary. Future upgrades to the Event Horizon Telescope, including adding more observatories and observing at higher frequencies, will sharpen our view, allowing us to create not just static images, but real-time movies of matter swirling around the event horizon. These films could reveal flares and hotspots, track the orbits of infalling gas clouds, and test the no-hair theorem, which posits that a black hole is defined by only three properties: its mass, its spin, and its charge. Any other hair or complexity from the star that formed it is radiated away. By precisely mapping the space-time geometry around the horizon, we can check for deviations from the predictions of general relativity that might hint at new physics. Other future instruments, like the Laser Interferometer Space Antenna, LISA, will detect gravitational waves, ripples in space-time, from black holes merging. These cosmic chirps will provide another, entirely different way to study the properties of event horizons and the nature of gravity itself. Each new piece of data, whether a photon or a gravitational wave, carries with it a clue from the edge of reality. Studying this frontier may unlock the deepest secrets of gravity, time, and the universe itself.